In our previous lessons, we were working with graphing linear equations and systems of linear equations. Now we're going to get back to some linear inequalities and looking at graphing those. So we treat them very similar to what we were doing with our linear equations. We want to make sure they're in slope-intercept form, and then we do the graphing, same process, finding the y-intercept or starting point, moving according to your slope, and then we have to set up our boundary line. And remember, for inequalities, when we were on the number line, the boundary point was either solid or open. Solid showing that it was included, open showing that it was excluded. And the same thing's going to happen here, except we're in two dimensions, x and y. And so for us, we're not just going to have a point on a number line, we're in a plane. So that boundary line would be solid or dashed, depending on the inequality symbol used. Remember, the solids were for the equal to portions with the inequality signs, and the opens were just greater than or less than. So the same thing will apply here. So again, our process would be, if we have to rearrange the equation in slope-intercept form, plotting our y-intercept and the slope, drawing our boundary line, and then shading the solutions. So if we look at our inequality, y is less than 4x minus 3, we can see it's already in slope-intercept form. And so we know our y-intercept is going to be at 0, negative 3. So we could plot that on our graph. And then we want to ask ourselves about the slope. And so our slope comes from the coefficient in front of x, which is 4. So think of that as 4 over 1, meaning we're going to go up 4 units and to the right 1 unit each time from our starting point, the y-intercept, to generate our boundary. So using our slope, again, going up 4 to the right 1, up 4 to the right 1, up 4 to the right 1, putting our points so we've exhausted our room on our graph. We can go back to the y-intercept and reverse it, going down 4 into the left 1. So we have a good series of 4 or 5 points here that we can draw for our boundary line. So for us, we're going to look at our inequality symbol, and it's less than. So remember, when it was just less than, the boundaries were not included. So for us, we're going to show that by drawing a dashed line. So now we want to think about the solutions to our inequality. And so just like we did before, when it was just on a number line, we picked a test point, and then we use that to see whether it was true or false. So for us, we want to pick a point that's not on our line and not on the boundary to test for our solutions. So if I look, a good one to use for us would be 0, 0. Why do mathematicians like using 0, 0? Because there really are not a lot of calculations have to happen if you're substituting 0 in for x and y for your inequality. So let's take a look. If we use that test point 0, 0, what happens to our inequality? While substituting 0 in for y and x, we now have 0 is less than 4 times 0 minus 3. Well, we know 4 times 0 is 0. Anything times 0 is 0. And 0 minus 3 would be a negative 3. So now we have 0 is less than negative 3. Is that true or false? Well, if something is less than, it's to the left of the number. So if you think of your number line here, here's 0, here's negative 3. Negative 3 is to the left of 0, so negative 3 is less than 0. 0 is not less than negative 3. That's false. Remember, we're not shading where it's false, we shade where it's true. So we're not going to shade on the side with the test point 0, 0. We're going to shade on the opposite side, okay? So we only shade on the side that's true. For us, that's going to be kind of to the right and below our line, if you're thinking of it that way. So we're going to shade in all our possible solutions. So anything to the right or anything below the boundary line, not included, because remember that's dashed, that's showing it's not included, everything to the right of that and below would be a potential solution. So if we asked you to name a potential solution to your boundary line, what could you? Well, potential solution could be 5, 0. It could be 10, negative 10. It could be 8, 7. Again, anything in the green shaded area would be a solution to this inequality. So let's take a look at another example. Here we want to graph y is greater than or equal to negative 2/3 x plus 8. So again, let's think of kind of our steps. Number one, rearrange the equation so you can graph it. As you look, I should say equation, your inequality. So you look at your inequality. Is it already in slope-intercept form or not? And we can see that y is already isolated, so we're good for the slope-intercept form. So since our inequality already is in the slope-intercept form, we're going to ask ourselves, well, where are we starting? What's our y-intercept? And if we look at our inequality, we can see our y-intercept is here, and that would be at 0, 8. So we're going to plot that point. And then we want to look for our slope, the rate of change. And again, that's your coefficient, the number in front of x, and it's negative 2/3. So remember, what does that mean? It's going down 2 units into the right 3 from your y-intercept. So down 2 to the right 3, put your point, down 2 to the right 3, put your point until you run out of room. You can always go back to your y-intercept and reverse the slope, going up 2 and to the left 3. So we have a good set of points that we could use to generate our line. Now, how are we going to draw our boundary line? Again, that goes back to your inequality symbol. We have greater than or equal to. Because it has the equal to portion, we know each of these boundary points could be solutions to our inequality. So we're going to have a solid line when we connect our points. Last but not least, we want to find all the solutions to the inequality. We have a sample here of the points on the boundary line, but we know there's an infinite amount in the region, so we want to find that. So again, we want to pick a test point, a point not on the boundary line that we could use to determine if it's true or false for your inequality. So what would be a good test point for us? Again, we could go back to 0, 0. So if we test 0, 0 into our inequality, what's going to happen? Well, let's see. As 0 goes in for x and y, we now have 0 is greater than or equal to negative 2/3 times 0, which we know is 0, plus 8. 0 plus 8 is just 8. So is 0 greater than or equal to 8? No, that's false. So since it's false, we know we cannot shade on the side of 0, 0. We have to shade on the opposite side. So we're not shading below our boundary line. We're going to be shading above it. So everything for us on the boundary line and above could be considered solutions to your inequality. So what could be a potential solution? Again, we could have that solution of 10, 10. We could also have a solution of 6, 4. We could have a solution of 3.5, 9. Anything in the shaded region or on the boundary line would be a solution to this inequality. So let's try another one. Here we want to graph the inequality 2x minus 5y is greater than 10. So again, let's think of our steps. So we have to rearrange the inequality to put it into slope-intercept form. That means the y should be isolated. For us, we can see that y is not alone, so we're going to have to do some work on getting it alone. So to start working on isolating y, we would have to undo the equation. So let's undo the positive 2x by subtracting 2x from each side. And then we'll have to divide every single term by a negative 5 to get y alone. So remember, a negative divided by a negative is a positive, so we'll have a positive y. Positive divided by a negative, that would be a negative 2. And a negative divided by a negative would be a positive, and we have a 2/5 x. Now, because we're taking the opposite of every single term in the equation, remember with inequality symbols, those get impacted. So we have to take the opposite of the greater than sign, and that's going to become a less than sign. So here's the rule that we need to graph. Y is less than negative 2 plus 2/5 x. So again, picking up where we left off, we know that it's in the slope-intercept form, so identify your y-intercept. Our y-intercept comes from here, and that would be at 0, negative 2. And then, once we have that plotted, we need to find the slope. Remember, the slope is the coefficient in front of x, which is 2/5, which means from this point here, we're going to go up 2 units and to the right 5 and put a point, up 2 and to the right 5 and put a point. We can go back to the y-intercept and reverse the slope, going down 2 and to the left 5 until we run out of space. We want a good 4 or 5 points to generate our boundary line. So once we have that, you're going to ask yourselves, well, what kind of boundary line do we need? And you go back to the inequality symbol, and we can see that it's less than, saying that the boundary points would not be included on our solution set. So we have to use a dashed line. Now, where are all the solutions going to be located? Well, that's our shading, and to figure that out, we need a good test point. So what is a good point that is not on your boundary line at all? So we want something above or below. And again, look, our test point here at 0, 0 would be perfect for that because it is not on our boundary line. So if we take 0, 0 and substitute it into, you could do the original inequality or the one that you have in slope-intercept form, we want to see whether or not it's true. So I'm going to go back to the original just in case I made a mistake in my slope-intercept form. And that will tell me, again, the shading part to be true. So if I substitute 0 in for x and y, we have 2 times 0, which is 0, 5 times 0, which is 0. 0 minus 0 is 0. Is 0 greater than 10? Well, we know that 0 is not greater than 10, so that is false. So we are not going to be shading on the side with 0, 0. We want to shade where it's true. So for us, that would be below our boundary line. Okay, so again, we're shading on the side where it would be true. That would be opposite for us of 0, 0. So everything below our boundary line would be a solution. So that could be at 0, negative 10. It could be at negative 10, negative 10. It could be at 8 and a half, 1/2, 8 and a half, negative 1/2. Any of these points in the shaded region, not on the boundary line, would be a solution to your inequality. How about this one? Graph the inequality y is greater than or equal to negative 3. So again, think of your steps. Do we need to rearrange the inequality to put it into a slope-intercept form? No, we do not. Y is already isolated. So can we plot the y-intercept and the slope? Well, looking at our inequality, we can see that our y-intercept would be at 0, negative 3. So we're going to start there and plot that point. Now, what would be our slope? Well, our slope is the coefficient in front of x. Now notice you do not have an x in your inequality. So that means it's a 0. So if you have a slope of 0, that means that you are not increasing or decreasing, you are staying at the same part, right? Y has to be greater than or equal to negative 3. So if that's your boundary, negative 3, that y has to be, we can put not going up or down, just right or left, keeping y at negative 3. So I plotted a series of points, kind of help you determine the boundary. Now that we have the boundary points, how are we going to connect them? Well, if you look at your inequality symbol, it says greater than or equal to. Again, equal to means that these boundary points can be included in our solution set. So we're going to include them by drawing a solid line. Now again, we want to pick a good test point not on the boundary line to see if it's true, because that's where we want to shade. If it's false, we shade on the opposite side because that would be where the true answers are. So again, for us, 0, 0 is not on our boundary. That would be a perfect test point to use. And let's put it into our inequality and see what happens. So we're going to put y as a 0. Is 0 greater than or equal to negative 3? Yes, it is. So since that's true, we're going to shade on the side that contains 0, 0. So everything on our boundary line and above could be a potential solution to our inequality. So again, you're shading on the side that's true. For us, 0, 0 worked, and that's why we're shading above and on the boundary line for our solutions. How about this one? Can we graph the inequality x is less than 1? So if we think about this, is this in kind of a slope-intercept form? And it is. We don't have a y, but we do have the x that's isolated. And so if you relate that back to when we were graphing our lines, when x equaled something, what kind of line did you have? Well, this is a vertical line because we have a slope that is undefined. So we don't have a y-intercept, we have an x-intercept at 1, 0. And again, it's saying all the x values would have this 1 as the input. So I can generate a series of points with that undefined slope to help me make my line. Now, how are we going to draw the line? Look at the inequality symbol. It says it's less than. So since there's no equal to's, we know that these boundary points cannot be part of our solution set, so we're going to have a dashed line. To find our solutions, we have to use a test point, something that's not on the boundary line, to see whether or not it's true. And again, we could use 0, 0 as a test point and see what happens. So if we put 0 in for x, what occurs? Well, 0 is less than 1. True or false? That statement is true, so we're going to shade on the side of 0, 0, so that's to the left of our boundary line. So everything to the left of our boundary line would be a solution to our inequality. So we've done a lot of review of graphing our inequalities, and it's just like how we were graphing our equations, trying to get it into a graphing format, slope-intercept form, or if it ends up being a vertical line where the x is isolated, and finding the solution set. Well, what if we went backwards? What if we knew the solution set? Could we write the inequality that goes with it? For example, here we have the solutions to our inequality. Can we write the inequality to represent that graph? So let's think about what's involved. Let's see what points we know on our boundary line. So I highlighted a few. Do we know the y-intercept of the boundary line? Yes, we do. We can see the y-intercept is here at 0, 3, so that helps us get going with writing our inequality. Can we also determine the slope from the points on the boundary line? Yes, we can. We can see that the line is increasing, so our slope is positive. And to go from point to point on the boundary line, we're going up 3 into the right 1. So we now have the slope and the y-intercept to start writing our inequality. So again, we said our slope is 3 and our y-intercept was at 0, 3. So what inequality could we start writing? Well, we know it's going to be y, an inequality symbol, and then we have the y-intercept and the slope. So we could write it as 3 plus 3x or 3x plus 3. And let's just put a box to hold the place for our inequality symbol. What we want to do, again, is to figure out what kind of symbol we can use. So again, thinking of a test point that we could use, we're going to substitute it in and see what occurs. So for us, a good test point could be 0, 0 again. And notice how 0, 0 is not a solution to our inequality. So when we put 0, 0 into this mock-up inequality, we want it to be false. Okay, and so we want to make sure it's not included. So we want to make sure when we write this, we're ending up with a false statement. So we put 0, 0 in. Let's see what happens. We simplify it, 0 something 3. And again, when we fill this in, it needs to be false. Well, we know in actuality, 0 is less than 3. So what kind of symbol would we need to make that false? Greater than. Also, look at the boundary line. It's solid. So if it's solid, that means we have to have an equal to as part of our inequality symbol. So we're going to throw in the equal to here. So again, this would be our inequality. Y is greater than or equal to 3x plus 3, or maybe you wrote it as 3 plus 3x. It's the same thing. Let's try another one. Again, we want to write the inequality represented by the graph. So look at the graph and try to plot grid points that you know the coordinates of on the boundary. So if we plot those points, I'm just going to circle them so remember we can see the boundary line is dashed, so they're not included. That's why they're open. And we can see that what would have been our y-intercept if it was included is at 0, 4. And how do you go to point on your boundaries? Well, we're going down. Now be careful here. We're counting by 2's for the y's and 2 for the x's. So we're going down 2 units and to the right 4 units. Well, 2 over 4 simplifies to a slope of negative 1/2. So let's do our mock-up of the inequality. It would be y, then we'll put a box for our inequality symbol, and then I'm just going to put 4 minus 1 half x, or if you want to write it as negative 1 half x plus 4, you're welcome to do that. So again, now we want to figure out that symbol. So what would be a good test point that's not on your boundary line? We can use 0, 0. And notice when we use 0, 0, it's in the shaded region, so it has to be true. So as we're putting in 0 for x and y, whatever we end up with, we need to make sure this inequality ends up being a true statement. So here we go. Putting 0, 0 into our inequality, what happens? Well, 1 half times 0, that's 0, and 4 minus 0 is 4. So we have to, again, think about an inequality that we're putting in to make this true. So how is 0 related to 4? 0 is less than 4. And again, since it's not included, it's dashed, we can't have the equal to, so we're just going to have the less than symbol. So what would our final inequality be? Y is less than 4 minus 1 half x, or if you wrote it as y is less than negative 1 half x plus 4, you are still on target. So as we were working with the inequalities, there were kind of 4 guidelines that we kept going back to. We always want to make sure the inequality, even so you're thinking about it as the equation from the past, but it's the inequality in slope-intercept form. Okay, so we're trying to isolate the y. And remember, for us, since it's inequality, where the equals is, that's going to be a inequality symbol, greater than, less than, greater than equal to, or less than or equal to. We want to find the slope in the y-intercept so we can start working on that boundary line. We know that it's dashed when they're not included. So if we see a less than or greater than symbol, if they are included, we use a solid line, so less than or equal to or greater than or equal to. Then we think about shading above or below, or maybe you'll think of to the left and right of the boundary line based on the test point being true or false. So you're going to do some more practice with graphing your linear inequalities and coming up with the inequality equation, we'll call it, if we give you the solution to the inequalities.